episode 120, Biggest Small Black Hole. Welcome back to another edition of the Syzygy podcast. My name is Chris Stewart, and we are back around the round table in the office of one Dr. Emily Brunsden. Emily, how are you doing?
I'm good. It's been a while.
It has been a while. I mean, it's not that long since we did an episode, although it did take me a couple of weeks to edit it. We did the live episode at the 10th birthday party of Astro Campus. Woohoo! Champagne corks popping and party buzzers buzzing and all of that. And that was great. We had a great time.
That was wonderful.
But I was looking back at the syzygy.fm webpage to see when the previous episode had been put up online, and it was like February or something. So I'm not entirely sure where the first half of this year is going, but it is going rapidly. So it's probably time for us to record another episode. Shall we do this?
Let's do it.
Today we are going to be talking about, well, I mean, it was something that actually came up strangely quite a lot at the Astro Campus birthday thing, because we did a Q&A right in the last episode. If you haven't listened, listeners, do go and have a listen, because there were some cracking questions that came up from mostly the young people in the audience at the live event. And most of the questions were about black holes. Turns out they have captured the public's attention. So today we're going to be talking about a black hole, one in particular that has made the news recently. Emily, what's so special about this one? What's going on? What's happened?
Wow, this is really exciting because they have hot off the press from GAIA data yet to be released even.
Wow.
We've got the detection of the biggest small kind of black holes.
The biggest small black hole.
Yeah.
Right. That's an interesting claim to fame, but we're going to have a little unpacking to do here. Okay, cool. First of all, who's done this? Whose name goes on this research today?
Yeah, so the paper came out in Astronomy and Astrophysics Letters, which is a really rapid way to just say, hey, we found this cool thing, let's just get it out there so people know without having to go through the slightly longer process of a full journal paper, which goes through peer review, and et cetera, et cetera. So
yeah, I mean, it's still real research. This is not substandard publication. This is legit. It's just fast track.
Absolutely. This is just stuff you need to know right now.
Yep.
So we got to get it out there as quickly as possible.
Cool. Okay. And who has done this?
So the paper has come from the GAIA collaboration. So the first page and a half are names on the paper.
You gotta love these big collaborations.
Yeah, we'll talk
Are
about
they alphabetical, or have they actually somehow figured out who did what in order?
Well, I didn't go into the deep, dark depths, but the corresponding author is the first author.
Right.
Who is Pascal Pauzot, who is from Observatoire de Paris.
Okay.
And
so it's Pascal et al.
Yep.
Yep.
And that what they've done is shown that from GAIA DR4 data, which is data that's not actually public yet.
Wow.
They've found this incredibly large, what we call stellar mass black hole. Largest we've ever found.
Right. Okay, well, as I said, there's a bit to unpack there. That's exciting, and clearly, I mean, it sounds cool, but it's also obviously exciting for astronomers because this has been rushed out of pre-release data, and we got to get this out there into the world. So we'll talk about that in a second. Just remind us though, first of all, GAIA. What's GAIA?
GAIA is
who is GAIA?
GAIA is a space telescope.
Ah.
It was launched in 2013, and its mission will run till kind of the end of 2025.
And what kind of space telescope is GAIA?
Well, I guess at its heart, GAIA is an astrometry space telescope.
Astrometry, so
Yes.
measuring the metra.
Yep.
Part is measuring. I mean, don't all telescopes measure? What is astrometry?
Well, a bit like meters, metra. It's measuring. Astrometry is the measurement or the precise measurement of the positions of objects in the sky.
So literally, like meters. How many meters away is this thing?
Yeah,
Not in meters, obviously, but yeah.
It's both. It's actually distance to objects, which is measured largely by parallax. So this is the effect where if you observe a group of stars or a star cluster or bit of the night sky, when you're in one position in the Earth's orbit, so let's say you do it in January, then you wait for the Earth to travel halfway around the sun and you measure it in July, the closest stars to you, what we call the foreground stars, will move against the background of the faraway stars.
Yes. And you're giving yourself a pretty good baseline there for that parallax by going from one side of the sun to the other.
Yeah.
So that's
So you
cool.
can measure the distance using that technique.
Yep.
But it also does very precise position measurements just in terms of, let's say, coordinates on the sky.
Right.
Now, that's not only what GAIA does a whole lot more of other stuff as well. It does colours, photometry, it does a bit of spectroscopy as well. So it's really out there to characterise largely stars, but lots of other astrophysical objects as well.
Right. Is it working in the visible, in the UV, the IR, the
Mostly,
orbit?
the GAIA band is mostly visible, so
Okay.
it's pretty similar to the visible. And I guess the point of difference is that it's not just doing this for a few stars. It's not even doing it for a few million stars. GAIA has about 1.2 billion objects that it's tracking.
Ooh, right. Okay. This is not mucking around.
Yeah.
Wow.
So over the kind of roughly 10, 12 years of its nominal mission, it will look at every single one of those 1.2 billion objects around about 70 times.
Wow.
And
Okay.
measure it.
It's got a big job.
Yeah.
Yeah. Doing well. Well done, GAIA, and all who sail with her. But that's background. Okay. The most important thing here is the black hole.
Oh, yes.
And this is, okay, we need to go back to this. This is the record. It's the biggest small type
Yes.
of black hole. Okay,
Yeah.
so we need to go through types of black hole.
Yes, I think so.
Which kind are we talking about and which kind are we not talking about here today?
Right. So you can largely say that there might be three types of black holes.
Okay.
The very, very smallest, which we're not actually counting here because we have no evidence that they exist, but they're a theoretical construct.
Okay.
Are kind of mini or micro black holes. So these are the kind of things that you might have heard inflammatory statements about, that CERN's going to make all these black holes, they're going to destroy the Earth, blah, 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 blah.
Right. You get enough concentrated energy in one tiny space, and someone really ought to do the maths on whether or not we're going to create a tiny little black hole here, which may or might, I mean, even if they do, may or may not be a problem. You know,
Well, clearly they're not
Yeah.
so far.
it hasn't destroyed the Earth at the speed of light. But it's like we don't know. We don't know whether these things exist. It's
No.
just maybe.
And if they do, they're not obviously impactful to
Yeah.
our everyday lives. So
Yeah.
let's kind of put them in the theory basket.
Okay, so that's a maybe.
Yeah, but those are little
Ignore those for now.
particle-sized and smaller
Right.
black holes. What we talk about real black holes, and these are real astrophysical black holes. You have two different sizes or size groups.
Mm-hmm.
The first are the stellar mass black holes. So these are black holes which are the size of the sun-ish. We're going to go up to maybe kind of 85 solar masses.
Okay, so sun, give or take,
Yep.
some suns. Yeah.
And they come out of the process of stellar evolution. We've also got supermassive black holes, which we've talked about a few times. And these are the massive, billions of times the mass of the sun, black holes that you find in the centers of galaxies.
Right. Okay, so we got quite a big gap between your supermassive. I mean, it's kind of in the name, right? It's supermassive. And it, like, are we always talking billions or
For big galaxies,
Yeah,
yeah.
okay. So billions of solar masses, big honking things in the center there. Some of those, if they're actively feeding, you know, we've talked a few times about things like quasars and active galactic nuclei and stuff like that. Big honking scary things in the center of galaxies. Big gap. Mm-hmm. Then what did you say? Up to maybe around 80 solar masses potentially?
Well,
for-
this is where
anyway,
it gets interesting.
stellar mass black holes,
Yeah.
which is sort of sun mass to dozens of solar masses.
Exactly.
Right? Okay. And then we're going to ignore the other kind.
Yeah.
Okay. So we're talking the smaller one.
Yeah.
Right? And this is the biggest one of those. So
Biggest ones that we've found in our galaxy.
biggest one that we found in our galaxy. Okay, there's so much to unpack
I
here.
know, yeah.
So how big are we talking? Let's get the stats out of the way.
Right.
How big are we talking?
So this one is 33 times the mass of the sun. Mm-hmm. So if you went and said, what are all the black holes that we know about in our galaxy? Number one, supermassive black hole in the center. Fine.
Yep.
Doesn't count when you're talking about
Push
these
that
ones.
one aside
Yep.
because nothing can compare to that.
This is
right?
now number two.
Yep.
Or number one if you're talking about stellar mass. 33 times the mass of the sun.
That's pretty funny, really, when you think about, okay, what's the biggest in the galaxy? Yeah, it's like billions Okay, what's the next biggest then? Like, it's got to be close to that, right? No, it's 33.
Yeah.
Hang on, what happened to all of those orders of magnitude in the middle there? Maybe we can come back to that. But 33,
Yeah.
okay, is number 2.
Yep.
Yeah.
It's also the second closest black hole to the Earth.
Wow.
Yeah.
Okay. What were the odds of that?
Yeah. Well, and that's where it does get interesting.
Interestingly,
Very
yes. Maybe we
interesting.
can come back to that.
Yeah. So if you want to talk about close proximity, the closest black hole is something called BH1. It's actually GAIA BH1.
I'm guessing that stands for Black Hole 1.
It is.
Hey!
It is. It was the first black hole that
What
Gaia
were the odds?
discovered. There you go. That is 1,560 light years away and has a mass of 9.6 times the mass of the sun.
Okay. Now, sorry, hang on. How far away did you say it was?
1,560. Yeah.
Light years away.
Light years.
Okay. We always have to do this, Emily. Give me some grip here on how far. Like, is that really close? Is that far away? It sounds like a long way away because it's light years, but I also know that space is really, really big. So, in terms of, okay, let's go with next star is how far?
So that's I have to convert from parsecs to light. About 3 and a bit light
Three
years.
and a bit light years.
Yeah.
Okay. And then what's the diameter of the galaxy?
So my always grounding point is that we're about 2/3 away from of the center of the galaxy. If you imagine it as a big disk, we are 25,000 light years or so from the center.
Okay, so we're 25,000 light years from the center of the galaxy. The nearest star is about 3 light years away. And we're talking about something which is 1,500 light years away. So that gives some sense of distance here. That it's a lot further than the nearest star, but it's still a very, very close thing compared to the rest of the galaxy. It's in our local neighborhood.
Yeah, exactly.
Cool. Okay.
Yeah. Yep, so that's black hole 1. And now, interestingly, black hole 1 is at 9.6 times the mass of the sun. Very typical mass for these types of black holes. We expect them to be 10-ish times the mass of the sun.
Okay. And
That's
why
fine.
is that? Because you've got to be big enough star to make a black hole in the first place?
Exactly.
Right.
Yeah. So we'll come back to that. But that's broadly the garden average size of stellar mass black
Sure.
hole.
It's a common garden variety black hole.
Yeah.
Good.
And then, so this one is 2,000 light years away.
So not much further.
No, only about a quarter again.
Yep.
And is 33 solar masses, so more than 3 times.
Yeah, three and a half times bigger. Which is a lot. Yeah. So,
Now, here's the conundrum. So, to get a black hole, you need to have a very, very big star that collapses in on itself. They're called core collapse black holes because the star gets so big and the mass gets so centrally concentrated at the end of the star's life, it just collapses down. There's nothing in physics that can hold the star up anymore, so it collapses to a black hole.
right. Does it go through any of the other phases? Like we've talked about all sorts of different ends of lives for stars before. You can make things like white dwarfs. You can make things like neutron stars. There's all sorts of things that you can do along the way, which involve, as we're collapsing down, you hit these limits of physics, which is, okay, well, you can't squeeze the electrons down anymore, or you can't squeeze the nuclear matter down anymore. But gravity can always overcome that. If you've got enough stuff, eventually you'll just get so concentrated and so energetic, so much gravitational energy that you just move past that limit onto, well, we'll just bring in the next level of physics now and we'll just create the nuclear matter. We'll turn all the protons and electrons into neutrons. Or we'll even go beyond that and just collapse completely into a black hole. When you're making a black hole like this, do you actually pass through those other phases and sort of stop for a moment and then, oh, no, we just keep going? Or does it just collapse down?
Well, sort of yes and sort of no.
Okay.
So you don't create a white dwarf star and you don't create a neutron star. But what happens is the core of these very, very massive stars is degenerate at some point. And that's that point where quantum physics says you can no longer collapse.
Yes.
That's it. So they do get to that degeneracy in the core. What's in the core at that time sort of depends on how the fusion process has gone for the star. But yes, they do have the degenerate core. Then you just hit the limit where the degeneracy can't hold the star up anymore.
But is there a sense that it's sort of like it pauses for a minute or 1,000 years or a second or a microsecond and then keeps collapsing? Or does it just whoosh straight on through it? Or do we not know?
Well, I don't know if we know all the details, but certainly the core sort of collapses very, very quickly. And the material in the outer atmosphere of the star takes a while to notice that that's happened. There's a communication lag, basically.
Yeah.
And so this is part of the supernova event at the end of the star's life. And so when that material comes down to hit the degenerate core, which it's just sort of fallen to, it will bounce off that degenerate core, and then that's your big bang outwards.
Yeah.
As the outer material goes in first, bounces, then comes out.
It hits this incredibly hard degenerate core and bounces off with incredible energy. Yeah.
And if your star was born with more than about 20 solar masses, then even the core itself can no longer hold itself up under neutron degeneracy pressure, the strongest pressure that we have, basically.
Yeah.
And that just then collapses to a black hole.
Physics has got nowhere else to go at that point. It's like we got nothing left. We can't hold you up anymore. You're just going to have to go.
Yeah. So broadly, all massive stars that are bigger than 8 solar masses will have a supernova. Any star that was born with more than 20 solar masses will have this black hole as their end product.
Okay.
Now, on average, the size of that black hole ends up being around about 10 solar masses.
Yeah, as you said before, that's your sort of common or garden variety mass of a black hole.
And that's roughly because, so when stars are formed, they're formed 20 plus. They're going to eject a whole lot of material of their stellar winds at the end of their life. So they don't go from being 20 solar masses as they're born to being a black hole of 20 solar masses. They lose, quite a lot of their material along the way.
Yeah. Presumably in the supernova at the end as well.
Quite a lot of it.
There'd be a lot
then,
being blown off. Yeah.
But even leading up to that, the stars become very unstable. They cast off a lot of material. So they just lose a lot of mass, basically. Right. So even if you're born with 30 solar masses or 40 solar masses, then you're still going to end up round about the kind of somewhere in the range of maybe 8 to 15 solar masses left as your black hole in the end.
And the black holes that we've observed so far, they tend to be clustered around that roughly 10 solar masses. Does that differ terribly much? What's the lower bound, and then how high? I mean, forgetting about our record breaker, we'll come back to that in a minute. But how low can a black hole go?
Ooh, that's a good question.
And how big do they tend to get?
So
what are the tails of this distribution?
I'm not sure what the actual minimum is for these black holes, but it must be around about 8, I would guess, something like that, solar masses, because that's your minimum. You need to start with at least 20, so you're probably looking at around about 8 solar masses.
Okay. But I mean, there's no physical limit, like with neutron stars, right? Neutron stars happen at a very, very specific mass when a star is collapsing.
Oh yes, no, you're quite right. So I think you go up to about 2 point something solar mass, 2.8 maybe solar masses, something like that, as your highest neutron star.
Right.
So it must be somewhere around there.
Sure. Okay.
Plus.
Okay.
So that range now. So where are we going? So I'm setting up the problem here, basically.
Yes. Okay.
So we can understand how black holes form in this kind of up to 10, maybe 15 solar mass range. The very extreme other example we have that's in our galaxy is called Cygnus X1. Mm-hmm. This is a black hole we've known about for quite a long time. This one is 21 solar masses. So this was the previous record holder for these stellar mass black holes. And already that was getting quite large.
Yeah.
For at least our modelling of how we understand these black holes to form. So that's kind of fine. We understand how to make those black holes. We broadly understand how they're formed. The problem is that when we turned on LIGO from, was it 2016? We turned it on.
Yeah. I mean, it's been going for much longer than that, but turned on with its special upgraded detectors. And this is so just to be clear, LIGO stands for?
Laser
interferometer, something, gravitational observatory.
Yeah,
this is the thing that's detecting gravitational waves, not gravity waves, that's a different thing, gravitational waves of big things go boom in sky, making space-time wobble, really, really tiny wobbles, which for many, many, many years after they were predicted from Einstein's theory of general relativity, It wasn't even clear whether or not we would ever be able to detect them. Turns out we can. And
Yeah.
in 2016, when they turned on LIGO with its new upgraded detectors and went, hey, wait, what's that? And they detected the first one, almost stumbling over it. It's opened up this whole new area of astronomy, which is we can literally look at gravity and see what that's doing. So that's really cool.
It's really cool. Yeah, so we can get gravitational waves from very high mass systems that are merging. This is how they produce kind of enough gravitational waves to be like hit our detector, basically.
Yeah.
So stars just sort of cruising around the galaxy are not going to make strong enough gravitational waves for us to detect. Even these black holes on their own are not strong enough for us to detect their gravitational waves.
Yeah, I mean, they are making gravitational disturbances, but it's just so minutely, ridiculously small. You need a really big boom in order to actually show up at all.
Yeah, and so we've been able to detect these really big booms, these really big mergers of black holes. So they're two black holes spiraling in closer and closer together. They merge, they produce a huge amount or huge intensity of gravitational waves, and it's those that we've been just able to pick up in our best detectors.
Which is a crazy idea, right? Like it's hard enough to imagine two neutron stars, which is another thing that you can observe with LIGO, and they definitely have. It's hard enough to imagine what that would look like. But now try to imagine for a moment what it actually looks like if you were able to get close enough to see two black holes spiraling around each other and merging. I mean, you wouldn't want to be too close because that's going to get ugly real quick. But what does that even look like? That's nuts. But we certainly do know from a gravitational wave point of view, we know what that looks like. We know what the signal is, which is cool.
Now, these are black hole mergers that are not in our galaxy. Let's be clear. We haven't had any of one of these in our galaxy because we would see that.
Right.
we would notice
that.
Yeah.
How would we see that? What would it like? Would it give out huge amounts of radiation?
Well, there'd likely be a really bright light to go with it because you're getting some of if there's any disks involved in the black holes, they're getting very superheated.
Yeah.
But like a supernova, really.
Yeah.
But we do see these other mergers. They're happening in other galaxies quite far away. But what we can do is from those gravitational wave detections is we can figure out what the masses of the two black holes are.
Okay.
And by and large, we're seeing mergers of black holes that are 30 up to 85 solar masses.
Right. So that's where your 85 came from earlier. So we're seeing, so there's so much going on here. We're seeing the signal of merging black holes, which are larger to much larger than the biggest things that we've seen in our galaxy.
And the biggest things that we know how to make.
Right. Okay, so there's two things there. First of all, bigger than anything we've seen. And so my immediate question is, well, are we just not seeing them in our own galaxy then? And the thing that makes me wonder that is the fact that the biggest one that we've just found happens to be literally next door, like it's the second closest one we've ever seen. The odds of that feel to me really quite small, which suggests to me there's actually lots more out there, bigger than that. We just haven't seen them yet. Does that sound plausible?
Absolutely.
Okay.
In fact, it's acknowledged, right?
Yeah,
these things are really, really hard to detect, and we'll talk about why they're so hard to find. But yes, there may well be lots of them at this mass all around our galaxy, and they're just really hard to spot.
Yeah, I mean, statistically, you wouldn't get your biggest one just there. Like it'd be miles away.
But we have spotted some,
Yeah.
And we have found quite a few in this, 10-ish solar masses. We still don't know how, we don't have a very clear idea how to make them a lot bigger. How do you make something 3 times bigger than all your models tell you it should be?
Let alone like 8 times bigger. Like, how do you get that? So that's the second part of your conundrum is like, where are they all in our galaxy? And secondly, how do you do that? And are there any ideas?
Well, yes. So let's go with the first one. How do we find them?
Good.
Because this is where GAIA is truly excellent. So GAIA is looking at the precision astrometry. So really very, very precise measurements of the positions of these objects in the sky. Now, problem is black holes, black.
Yeah. So this was going to be my next question is like, how do you find them? Like supermassive black hole, center of the galaxy, you can see loads of stars whipping around at ridiculous speeds around something. you can't see the thing itself, but you can see its effects on all the stars in that center of the galaxy. You know it's there, and you can work out how big this sucker has to be. That I get. How do you spot a 33 solar mass black hole 2,000 light years away, Emily? How's that work?
It's actually the same process.
Really?
Just on a smaller scale.
Okay.
So the great thing about these very high mass stars that form black holes is that they're very often formed in binary pairs or trinaries or even more. They've got got friends, they've got companions.
And why would that be?
It's because of the way that if you're going to form a very high mass star, you need a very dense, massive cluster of cloud and gas. And so the actual formation process just means that naturally the fraction of stars born with a companion, I think for these most massive stars, it's over 80%.
Wow, okay.
Are born with 2, 3, 4, 5, whatever stars in their system.
So it's just simply that there's more stuff around, and if there's more stuff around, you're making both bigger stars and more stars.
Yeah.
Right. And if you've got more stars in a small space, they are, by their very nature of gravity, are going to be going around each other. Yeah, okay, that makes sense.
And this is very useful because then we can pick up the existence of black holes by looking at companions, measuring how the companions are orbiting this unseen object.
Right.
And then figure out what the black hole's doing.
That makes sense. So it's another case of we're inferring what the thing is by looking at what the thing next to the thing is doing.
Yeah.
Yeah, okay.
So in the case of Cygnus X1, which I mentioned before, it's actually an X-ray binary. So we actually detected the X-rays coming from it. And this is because the binary is so close, there's actually material transferring off the companion star, which is a big, bright blue star, very, very big supergiant star. And there's material coming off that and feeding into the black hole.
Oh, okay. And so because the black hole's gobbling it up, that's a pretty energetic event in itself. And so there's lots of really high energy photons or X-rays coming off, and you could detect that. Cool.
So that's one way. If they've got a feeding black hole, they're typically easier to find. However, if they're not feeding, then you can look at the very precise motion of the companion star and see, hang on, this star's not just cruising around the center of the galaxy on its own. It's doing its own orbit around or with some unseen companion.
Right. So it is very much like the supermassive black hole in the center of the galaxy, just as you say, on a smaller scale.
Indeed. Yeah. So this is how we find what you might call quiet black holes. Or not feeding black holes.
Not feeding. Quiet, content.
Yeah.
Contentedly resting. Yes. And how, so you can, from the motion of that star, I guess you'd need to know the companion star or stars, you'd need to know how massive they are and what their motion is to then work backwards and figure out, well, if they're moving like that and they're this big, then the other thing must be this big. And that's where your 33 or however many solar masses would come from.
Exactly.
Right.
Yeah. So this is where GAIA just excels because it's measuring very precisely these positions. In fact, it's estimated that GAIA is going to increase by 2 orders of magnitude the number of these detected binary systems.
Wow. That's a lot.
That's, 1,000 times more than what we already had.
That's a good day's work, Gaia.
Yeah.
Nice work.
Yeah, well done. So what was really exciting then about this one is that what the team were doing was they were looking through what we call data release 4. So we've had data release 3 from GAIA. And these are GAIA doesn't work as in it's not always beaming data down to everyone to just pick up.
Okay.
Some telescopes work like that. TESS works like that, where the data comes out basically a month or so after it's observed and it's just there and everyone can download it and you can download it tomorrow and have a look at it. Other telescopes are done slightly differently, where they might be treating the data a bit before they release it, a bit more intensely. Or in the case of GAIA, there's also a proprietary period where the people involved have it first for a little while.
That seems fair.
Yeah, and then they let everyone else have it.
Let's have a play first, and then you guys get to play. Yeah.
So DR4 is probably the most important data release that GAIA will have, because this is the full 5 years of the first part of the mission. So 2013, 14 to 18, 19. So 5 whole years of data. We've only had 1 effectively so far. And it's basically everything that GAIA can do. It's positions, it's colors, it's temperatures, it's the motion of every one of these 1.2 billion objects. It's the 70 odd observations that we've made of it. There's just so much information. It's almost overwhelming.
So hang on a sec. correct me if I'm wrong, this is 2024 now, right? And we're about to have data release 4, which is 2013 to 2018?
Yeah, it takes a while to
Wow.
process.
That's-
Yeah. Well,
wow.
actually, we're not going to get data release 4 this year. We're going to get it towards the end of next year.
Wow.
So they're still
That's
working
a
on
lot of
processing the data.
messing around with.
Yeah, but there's lots of things going into it. So a lot of code being run on it to pull out interesting objects, to automatically classify a whole lot of objects. And it was during the testing of one of these pieces of code that was testing the capabilities of GAIA to just. So it's not so much that the data just gets dumped on you, and you've got to then sit down with your pen and paper and figure out, well, okay, well, if you take this equation and you use some gravity from here and you use Einstein, you don't have to do that. It's all done for you. All the equations are built in, all the detections built in, so that you get not only here's a binary system, but you get a full solution of the whole orbit, and all the information you need.
So when you say a data release, you don't mean, okay, here's all the ones and zeros from GAIA's hard drive. You mean, no, we've churned through this. We already know at least the raw details of what we've got in here. Now you guys go and explore.
Yeah,
that's what you mean.
Exactly.
Okay.
And it's very
no
carefully
wonder
curated.
It takes a long time.
Yeah, and it has to be calibrated and checked and put against other benchmarks to make sure it's accurate.
Take all the aliens out.
Yeah, that's useful. But yeah, so it takes a while. So during the testing of this code it has in the previous data releases and is going to be included in data release 4, the code that checks all these binary systems, they just serendipitously came across the system and it just threw up this number of 33 solar masses.
Wow,
so
that's
the team
cool.
thought, okay, that's odd. We should probably check this.
Yeah. Stop and just have a look at that one for a minute.
Yeah. And so that's exactly what they did. Did a whole lot of follow-up ground-based observations just to say there's nothing wrong with the data. Let's just double-check it. We'll do some spectroscopic measurements. We'll do some other astrometric measurements. And, all checked out. And this is exactly what the system is telling us.
Cool. That's beautifully serendipitous. Like the parallels with LIGO. Quite wonderful that we didn't mean to discover this thing. We were just testing.
Yeah.
We were just looking at stuff and there it is. So that's cool.
Yeah.
Okay, so we've got an accidental tripping over. Just it's only the largest stellar mass black hole in the galaxy. So okay, fine. Well done, GAIA team. That's really exciting. Presumably, there's going to be loads more of this stuff, and maybe even bigger ones in the data, but we'll see. But that's kind of looking at one side of this whole conundrum that you've been spelling out for us today, Emily, which is how do you find these things? And we've got a bit of a better idea of how you do that. You point special machines to look at the sky in great detail and measure very, very carefully, not the black hole itself, but the thing that's near the black hole. Great, understand that. But then we've got the other bit, which is, LIGO, that gravitational wave machine, was detecting things which were much bigger.
Yeah.
So there's a gap here that we need to plug. How do we move in that direction? What do we learn about that?
Yeah, well, even the 33 solar mass black hole that we have literally detected with our telescopes and indeed, seen, I guess you've seen the companion, this is already difficult to explain.
Yeah.
So stars just shouldn't produce black holes that are this big.
Presumably, if that's what's left over, the original star must have been huge.
Yeah. So
and
stars,
is that allowed? Can you do that?
Well, yes and no. So you can have very big stars. You can have 80, maybe even 100 solar mass stars if you really want.
Is that kind of your upper limit? Like we don't see them beyond that?
Yeah.
Okay.
Yeah. And that's fine. You can make those very, very big stars. The problem is that those very, very big stars in all our models will shed huge amounts of material in their late stages of evolution. So they just, their mass doesn't go into the final black hole. It just gets blown out in massive, angry stellar winds throughout the star's hydrogen fusion lifetime. And then it gets even worse when it turns into a red supergiant. It just loses all this material. It just can't hold on to it.
We talked about that a while ago when I can't remember exactly which episode it was, but you were telling me about some of these just stupidly big stars where the boundary of the star is not even like where does the star end anymore? It's just so nebulous by the time you get out, and it's just losing stuff. And that's before you even get to the violent. Let's just start chucking things off. And so what you seem to be saying is that even if you started with 100 solar mass star, there's no way that that's going to then turn into like a 30, 40 solar mass black hole, let alone an 80 solar mass black hole. So what? We've broken astronomy? What happened?
Well,
what's going on?
Unless, the magic word, I guess.
Yeah.
Unless your star has almost no metals.
Is this the astronomical version of metals?
Of course it's the astronomical definition of metals.
Just a little reminder to listeners that in astronomy, you've got hydrogen, helium, and then everything else. And the everything else is, quote, metal, end quote, which to chemists everywhere is like, what are you talking about? That doesn't make any sense. But to astronomers, like, look, it's just a collective noun for the other stuff that's less important. Okay, cool.
Yeah.
So, and you're saying unless you've got stars which don't have much astronomical metals in them, in other words, they're mostly, completely hydrogen, helium?
Yeah, basically.
Right.
Yeah. So we have some idea of what these stars might look like because we see them in the very, very early universe, right? Before the metals could be produced in earlier generations of stars, the first generations of stars were just pretty much hydrogen and helium.
Right, because that's what came from the Big Bang. We got all the hydrogen, maybe a little bit of helium from the Big Bang.
Yep.
And that's all you've got. You haven't got anything else. So that's what the first stars were. And then when they go boom, you make all sorts of other stuff.
Yeah, and we talked about how big they could be, which was...
Oh, yeah.
yeah.
That's right. We talked about that back in, like, was it 116, episode 116, Black Hole Sun?
Yeah, only like 3 episodes ago, but a couple of months ago
But
now.
it's like a lifetime ago.
Yeah.
These what were they called? Quasi-stars?
Quasi-stars, yeah. So they were about up to a 10 million solar mass.
Which is insane.
Insane things.
So you can do that with these. I mean, in that case, those earliest stars, can you still get them now? Is that...
Well, not directly just pure hydrogen, helium, maybe a bit of lithium stars. But if you have stars with low metallicity, then you could potentially build remnants of black holes, which are of this kind of 30, 50 solar masses.
Right. And is that because stars which don't have much metal in them just generally get bigger, or is it because the way they fall apart at the end of their lives is different?
A bit of both. So metals change everything about a star. So they change things like the opacity or how difficult it is for the star to radiate its photons away.
Right.
It can change the convective processes because it changes how the material moves from the center of the star outwards. So there's lots of just physics that changes when you've got even a little bit of metal.
And all of those things changing the way energy flows and towards the end of a star's life, it's all about how that energy is flowing. It's all about these balances, and at times incredibly delicate balances between energy coming out and gravitational collapse going in. So yeah, I could see how that could make a difference.
So broadly, stars with this low metallicity lose less mass.
Okay.
So that means that they will have a larger black hole as their remnant.
There's more stuff left over. Yep.
Now, this is something we can test because remember what we said about high mass stars like these, they tend to form in binaries, which is how we detected this star. That means that the binary formed pretty much at the same time from pretty much the same stuff.
Makes sense. Yes. Yeah, because that was the whole point, was if you're going to make a big star, you're going to make multiple big stars, and it's all from the same stuff. So presumably, roughly at the same time.
Yeah. So let's think about this black hole's companion.
Okay.
It's what we call an old metal poor giant.
Right.
So it's very old.
I'm pretty sure that was a kid's book.
Yeah. It's very old. It's around about 13 billion years old. So it's been around for a while, which also tells you that it should be metal poor because when it was born, there weren't metals in the universe to be born
Metals
with.
hadn't been done yet.
Yeah, exactly. It's around about 0.75 solar masses, so 3/4 the mass of the sun.
Okay.
And it's quite a big giant star. So it's finished its main sequence, normal fusion part of its life, and it's kind of just reaching those end giant points.
It's in pufferfish phase.
Yeah.
Yeah.
Yeah. Now, we measure from the spectrum of the star exactly what the metallicity is. So what that means is what fraction, if you like, of the elements in the surface and therefore in the star are metals. And what we do is just compare it to the sun. We say the sun is 1, and we can say
The sun is normal
Yeah.
for us. Yeah.
solar metallicity. And, if it got twice the metals or you got half the metals, whatever. This star has 1/288th the number of metals. as
That's
the
not
sun.
very much.
No.
That's a very, very small number.
In fact, that would be a very metal poor star. So just doesn't have anything that's really beyond hydrogen and helium.
Wow. So this is sounding plausible then. It sounds like we're on the trail of, okay, well, we can kind of see maybe why this black hole is so big is because it was metal poor.
So this is the link, right? So
Yeah.
we couldn't form these big black holes from stars that we see born in our galaxy today because they're born out of material that has a much higher metallicity from earlier generations of stars. But if you go rewind the clock a bit and think about what was happening when the first stars in our galaxy were formed, lots of these were very metal poor, and therefore they have managed to form these much larger stars and therefore these much larger black holes.
Makes sense. Makes sense. Sounds like a plausible explanation.
Yeah, and this is the first direct piece of observational evidence we have that links metal poor to large black hole.
Cool. I like it. And would that, do you then extend that to, so that explains the LIGO results as well? Like, we're not just talking about the 33 solar mass black hole that we've seen now, but we'd be happy applying that to 85 solar mass black holes?
Well, we might not have to reach that far because I think it would be a stretch to say, okay, we can't make a single black hole on its own out of that's 85 solar masses. But let's say we could form one that was 10, 20, or 30, say even. Or even let's push it even further. Let's say we can form one that's 40.
Oh, let's
solar
push the
masses.
boat out. Let's do
Right,
40.
on its own.
Okay.
Right?
Yep.
From this metal poor star. It only then takes 2 of those to merge.
Yeah.
And then you've got your 80, whatever, solar mass black
Yeah.
hole.
Even if you lose a whole pile through a great honking explosion, you're still going to have a lot.
Yeah.
Yeah.
That's a lot of an easier thing to believe would have
Sure.
happened rather than taking 8 black holes and saying, you just kind of get close enough together, all 8 of you, all at the same time, and sort of figure out how to merge.
Yeah, that kind of makes sense. So what you might be seeing at LIGO in one of these detections of the merger of 2 black holes, both of which are much bigger than anything we'd seen previously, like we see around us, that actually might be maybe a second generation merger. That you could already have had a couple of black holes merged together to make, say, an 80, and then there's a 50, and then that's merging. So this is not the first time that's happened to those black holes.
Maybe not.
Something interesting happened that we didn't see earlier, and now we're seeing the next one.
Yep. Or maybe even the whole system evolved on what we call a common envelope. So it was kind of like one mega stellar envelope that encompassed what was previously 2 stars as they were too close together. And then that went on and created the very large black hole. That's also a possibility. In fact, it's quite plausible that this object wasn't... There's been some interaction, we think, between the now metal poor giant star and the black hole. There probably was some interaction between those 2 atmospheres at some point in their evolution.
Turns out things are rarely as clean as you think at first sight. There's probably shenanigans going on at some point.
Yeah, and these massive stars, they do unexpected things because they just are so different to the sun.
Yeah. It's weird because on this podcast, we often come back to what's my mental image of the universe, and it's often a very simple one. But I imagine because they're like, you look up at the sky, Emily, and you look at stars, and they're tiny little dots. And so in my mind, I'm imagining if I could zoom up on it, I'm just looking at just a sphere of stuff. And that's a very simple thing to me. You know, big hot sphere of very nicely behaved stuff in space. But turns out it's actually often a lot more complicated than that.
Yeah, because you have this extra dimension of time. And time does interesting things to stars as much as it does to people. I mean, let's say you grabbed a population of people and you looked at, there were different people of all different generations there. There were people who experienced, let's say, the Second World War. There were people that experienced COVID. There were people that were born after both of those things. All of those people have very different experiences, which change fundamentally their makeup. And it's kind of the same way with stars, right? When you add that dimension of time, you start to appreciate that you can't have one set of sort of physics that explains the here and now of everything without considering how things have changed over that depth of the history of the universe.
It's like the historical social anthropology of stars. I love it. Well, Emily, we've done a few episodes over the last, well, this is episode 120 that we're on now. So over the last 120 episodes, we've done quite a few about black holes. But I like this one. This one's been fun. I'm still scratching my head a little bit about the exact nature of this record that we've just set, which is the largest of the smallest, but there's probably more, so it won't be. But I don't know. We'll take that for now.
I think we'll have to wait for the full DR4 and then we'll be able to trawl through this amazing data set.
I think the point is astronomers aren't getting really excited about the fact that it is the biggest and it will always be thus, just that, wow, that was unexpected. Cool, look at this. Which, when it comes down to it, is what it's all about anyway.
Yeah.
So that's cool. Listen, Emily, if people wanted to get in touch with us, like our lovely young question askers at the live event that we had the other week, and ask their own questions, whether they're about black holes or literally anything else in the universe, how do people get in touch with us? Can you still remember? It's been a while.
No, I definitely can remember.
Good.
We've got to jump onto syzygy.fm.
Yes, that's the best
our
place.
Wonderful website. It's got a little contact us form, and you pop in your questions. In fact, I'm going to start popping in my questions in there, just about the universe, and see what comes up.
You're going to be using our website as a little notebook from now on. And those emails come to me, and then I'm going to say, Emily, why are you doing this? This is silly. Just write them down. But no, listeners, you can do that too. Send us an email, send us a message through the website, but you can also get us on some of the social medias. We are on Facebook. Just go to facebook.com/syzygypod. Turns out that works. That's a thing.
We actually have a URL.
Well, yeah, that's a thing.
How many years has it taken us to realise that?
It took us a long time to work out how Facebook works. We're also on Threads occasionally and Instagram slightly more occasionally. But we are out there. And if you want to contact us, that's the best way. Look, if you want to support the show, there's a bunch of ways that you can do that. And the best way is to tell everyone you know that there is this thing called Syzygy, where two absolute space nuts talk about everything in the universe. And you can share that around with people in your life that you think would get a kick out of that. So that's number one. Number two is, if you want to support us financially, head over to patreon.com/syzygypod and throw a couple of pounds, dollars our way every month to help us keep the electrons flowing through the website and the lights turned on here at Syzygy HQ. Otherwise, I guess we'll see you in, give or take, a week. Let's try to get back on this schedule for as long as we can.
Let's do it.
So until then, Emily, catch you next time.
See you later.
Bye, everybody.